Do you have a test today?
Yeah.
How'd you do on it?
Not graded yet.
No?
No.
Okay, what are we going to go over tonight?
See what's next in the book. It's like polynomial functions.
Okay. Let me open my algebra book to the polynomial function section. So probably properties of exponents. Adding, subtracting, multiplying polynomials, evaluating and graphing them, factoring them. Finding rational zeros. Are you dealing with third degree polynomials?
I have no idea. It's the first time I've seen the damn things.
Okay. Let's talk about exponents. What is this equal to?
2 to the 4th.
Okay. And this?
2 to the 21st.
Ah.
2 to the 12th.
Okay. The rule here is that if we have the square root of a over b, it's equal to the square root of a over square root of b. So this would be 3/2. In other words, the square root of 9 over the square root of 4.
Okay.
But hold on, that's not really what I meant to cover. You have those three primary rules of exponents. Okay, this is what I meant to do. Let me think for a moment.
Let's be x3, y3.
Well, this is x to the third times y to the third.
xy to the 6th.
Xy to the third.
Oh.
In other words, it's a to the x power times b to the x power. Different bases, same exponent, is ab to the x. And the very last rule that you need is a to the x divided by b, something different, to the same exponent, is a over b to the x.
Okay.
So those first three rules of exponents that I tested you on and you knew, plus these two here. And that'll get you a long ways through. Oh, one other thing. Let's talk about negative exponents. Understand one thing about negative exponents? Has nothing to do with negative numbers.
Okay.
What is that equal to? The negative exponent merely means take the reciprocal. Put a 1 and put everything you see with a positive exponent below. Okay? So what is so what's the first rule you want to apply?
The one within the parentheses?
You can do it either way. I don't have any problem with that. So that would make it what?
1/2.
Squared, which is equal to
Equal to 1/4.
okay. And the other way that we could do it would be to do the multiplication of the exponents first. So we get 2 to the minus 2, which is the same thing as 1/2 squared, which is the same thing as 1/4. So with these rules of exponents, you can do in lots of different orders, and they all lead to the same answer. Here, let me look at something else, see if there's anything else. What's this equal to?
1.
No matter what x is? Trick question, yes.
Okay.
In other words, I'm looking through my book to see if there's anything interesting here that I'm omitting. Yeah, here's a cool one. R over S to the minus fifth all squared. So let's go ahead. So we're doing exponentiation here. In other words, we've got something that's already raised to an exponent and we're raising it to another one. So let's apply that first. What do we get? To top and bottom?
2.
R squared all over S to the minus 10, right?
Yeah.
Okay. Now what is R squared over S to the minus 10? When you have a negative exponent in the denominator, what do?
Put it in the numerator.
And change it to positive. So there's our answer. Okay, how about something like this? These are actually pretty easy. If you memorize those rules for exponents, these become simple addition, subtraction, and multiplication problems.
The x squared, y to the 4th. Oh, there's more.
That's okay. You can do it, like I said, lots of different ways. Okay, so there's the numerator. I think the easiest way to do these is to just subtract exponents, just like you would if it was A and B.
Okay.
So the x is what?
-1.
And the y is what?
3.
What is 4 minus a minus 1?
Oh, 5.
Notice that if this was a plus 1, then this would have to be to the third, so it can't be y to the third when it's a minus 1. Now, a lot of times here they'll say, do not leave any negative exponents in your answer, so what would this translate to?
Y3 over x to the first.
Y5 over x? Okay.
Yeah, that's right.
Let's see. This should be, if your book is anything like my book, this should be the first part of this chapter coming up. These problems that we're looking at here. Trying to find any that are more interesting, because these are getting a little easy. About
once you have, won't that equal 1 over 11 squared?
Yep.
Times 1.
Uh-huh.
Equals 1 over 11 squared.
Yep. Okay. Here's one that looks interesting. I don't know why they put the 1 in there, but I'll put it in there since they did.
So you have 36.
Well, let's not turn it into numbers. That makes the problem too easy. In other words, what they're looking for here is to use the properties of exponents to solve this.
Okay.
So first of all, let's take this. This would be the same as x squared over x to the minus 2. I can operate on that. So what is that part equal to?
4.
6 to the 4th, okay. And then this part here becomes, whoops, sorry, hold it, back up. I didn't do my order of operations properly. Don't want to operate doing division before we do multiplication or exponentiation. PEMDAS, the E is for exponentiation, so we have to do this first. So let's first of all translate it to that. So we have 6 squared over what? Apply this minus 2 to both of these exponents.
Minus 6 minus 4.
No. Minus 2 times minus 2 is plus 4.
4 times 5 minus 2.
Okay. Now we don't want any negative exponent. Well, let's go ahead and simplify it with negative exponents. So we have 6 to the minus 2 over 5 to the minus 2 Now, if I say now, get rid of the negative exponents, what does this become?
5 squared over 6 squared.
Now if you want to multiply it out, that's fine. Okay. How about this? What do we have? We have same base, different exponents. What do we do with same base, different exponents?
Add them.
So we make the base the same and add the exponents. Is that equal to?
1.
Looking. Well, it's hard to find a hard one. Once you know how to do these, none of them are really hard. You agree? I mean, so do it a variable at a time. What's the x going to be?
1.
What's the y going to be?
2.
Okay. Is this new stuff this semester for you?
Relatively.
Is it?
Yeah.
Synthetic substitution is my second subchapter of the polynomial chapter, evaluating and graphing polynomial functions. Is that coming up for you in this chapter? Can you see in your book?
Next thing is classifying polynomials.
By their degree?
And by number of terms.
Okay, I've never heard of classifying them by the number of terms. Let's talk about classifying them. In other words, if you have an x squared, you have a quadratic.
Okay.
Doesn't matter, well, I mean, you can either have another x term and a constant, or just x squared plus 1. That's a quadratic. Or the moment you write x squared, it's a quadratic, as long as you don't have a fractional exponent above the x. In other words, that would not be a quadratic function there. A fractional exponent means cube root. You have cubics, where the maximum exponent is 3, and you have quartics, where your exponent is 4. Now, believe it or not, cubics and quartics are incredibly difficult to solve manually. And the reason is that there's no quadratic equation for a cubic function. No matter how complicated a quadratic is, whether I can factor it or not, I can always plug it into the quadratic formula to solve it. Cubics and quartics aren't that way. In fact, it was only like 200 or 300 years ago that they figured out how to solve them. And that solution's called the radical solution. I don't even know how to do that solution, but the way we solve them today without calculators or computers is very, very manually intensive. You basically come up with 15 or 16 possible solutions, and then you try each one of them using synthetic division or synthetic substitution. Let's cover synthetic substitution or synthetic division. Have you done that this year yet?
No.
Let's cover it. That's something that'd be worth you having a head start on. Let's see. If I do this, if I divide x minus 1 into x squared minus 1, since that's difference of squares, I know it factors into x minus 1 times x plus 1. So I can divide this manually. I would divide the x into the x squared to get x, and then I would multiply that by both terms, and I would have a dummy variable here, so that now I take my dummy variable, subtract x, I got x minus 1, that divides into that plus 1. So that's how you do long division with polynomials. Now let me show you how to do synthetic division. Instead of dividing it by x minus 1, the only thing that really matters is these coefficients. And I want to divide by not the factor but the solution, which would be x equals 1. So I would use the 1 and put it in that little funny place. And then I put the coefficients up here, and the coefficients are 1, 0, minus 1. In other words, that 1, this 0, and this minus 1. And then, instead of subtracting like we do with long division, I'm going to add. First of all, I'm going to drop the 1. I'm going to multiply 1 by 1 to get 1. I'm going to add these to get 1. I'm going to multiply again to get 1. I'm going to add those to get 0. That means that I didn't have any remainder, and my solution is x plus 1. So if I want to know how to divide x squared minus 1 by x minus 1, I can do it synthetically this way. Eliminate the variable, just use the coefficients, and it gives you the answer. In other words, this is the coefficients at the bottom are my answer, x plus 1. That's the coefficient of the x term, that's the coefficient of the constant. So that's synthetic division. And the reason we use it is because it's so much faster to add as opposed to subtract. And also, when we do it by hand, we don't need all these variables. They're not actually part of the solution. The only thing that's important is their coefficients. Okay, let me give you an example and have you synthetically divide it. We're going to synthetically divide 4 into 3x squared minus 2x plus 10. In other words, this is the equivalent of dividing x minus 4 into 3x squared minus 2x plus 10. Only we're going to do it synthetically. So what's the first step?
I have no
Follow me.
idea.
Okay, let's go through it again. You take the very first line at the top left and drop it all the way down. After that, it's always multiply and add, multiply and add. So now we multiply 4 times 3, that's 12. We write it there, and now we add minus 2 and 12. What do we get?
10.
Now multiply 4 times 10.
40.
Add 40 and 10.
50.
That's the remainder. So since we got a remainder, x minus 4 is not a factor of 3x squared minus 2x plus 10. For it to be a factor, this has to come out to be 0. If this would have come out to be 0, then the answer would have been 3x plus 10 would be the other factor. And this applies to whether we're doing quadratics or cubics. In other words, I can also divide x minus 4 into x cubed minus 2x squared plus 4x minus 5. And the way I would do that, synthetically, list the coefficients across the top. 1 minus 2, 4. I don't need any dummy ones because every term is accounted for. Okay, let's try this. First step.
Uh, 4 times 1?
Yep, I drop the 1 and then multiply 4 times 1, put it there. Now what?
4 times negative 2.
First of all, we add.
Add.
So we get 2. Now 4 times 2 is 8. Now we add again. We get 12. Now 4 times 12 is 48. We add again. We get 43. Since that's not 0, that's not a factor of that polynomial. The key here, the reason you have to do this so much and why I'm spending time on it, is that when you have cubics and you're trying to figure out how to find the zeros, you have to figure out the factors. The factors involve a lot of trial and error division. So you might have to take a third-degree polynomial and try 6 different solutions until you get a 0 here. And only when you get a 0 for that last step in the synthetic division is that one of the solutions. And once you get a 0 here, the rest of it is this. In other words, that would be x squared plus 2x plus 12. If this were one of the factors of that third-degree polynomial, this would be the result of it. Only if you get a 0 for that. So you have to do a lot of synthetic division when you're trying to find factors of these higher degree polynomials. Okay? Well, if you don't have any other specific questions about this, I'll let you go.
Okay.
All right? I will talk to you next Monday. Have a good week.
You too.